Hello and welcome. Today we're going to be looking at the unit test for parametric equations and polar coordinates, one of the topics on AP Calculus BC. This one is not an AP Calculus AB, this is solely a BC topic. In this, we're going to look at all of these questions to make sure you understand how to approach and to solve the questions in parametrics and polar coordinates. I know this is a very hard topic, so let's get right into our first question. Let's go. Let R be the entire region enclosed by the polar curve r equals 1 plus cosine of theta. And we're asked to find the area of R. All right, how are we going to do that? Well, let's draw a line here. All right, so we can just find this area and then multiply it by 2. Okay, so 1 plus cosine of theta. Okay, so when theta is 0, then we get this right here. Okay, now when theta is pi, we get this. Okay, so take my calculator. We're doing an integral from 0 to pi of the curve 1 plus cosine of theta, 1 plus cosine of theta squared. Right? This is how the formula works. So you do the pi to 0 to theta, 0 to pi of whatever of your r squared, and then you have to multiply by 1/2. Okay? Multiply by 1/2. It's 1/2 times the integral from whatever of the radius squared. That is always how you do the polar coordinates, the polar functions. That's how you do the polar integral. All right, so I know it might be a little confusing, right, to do it that way, but that is just how that is the formula we use. That's the formula we use for trying to do this kind of stuff, right? That's the formula we use to find polar equations, right? If you don't know it, be sure to check out other resources there are resources on Khan Academy. There are lots of resources online where you can learn how these formulas work and how to apply them. But here we're just going to go through some problems, right? So we have first make sure you set it to polar. All right, you see it says right there, it says polar, POL. Don't leave it in function, FUNC. Don't leave it because it won't work there. Right, then you go to math, you do the integral from 0 to pi of 1 plus cosine of theta squared d theta. All right, and then divide that by 2. And you get 2.356, but that's just for the shaded area. And you have this area that's going to be the same area. So then you multiply this by 2 again, and you get 4.712. 4.712. And we can move on to the next problem. Let f be a vector-valued function defined by f of t equals ln 4t, 3 log 2 of t. Okay, so I'm going to go to mode, and I'm gonna think about this for a second. I'm gonna realize that I've been given a vector valued function, meaning that I am in polar coordinates. Right, so I'm going to polar coordinates. Polar coordinates are the ones right here. This is this is parametric coordinates. We were in polar. Now we're dealing with parametric functions. That's the one right there. PAR, parametric. All right, now how does that help me? Well, first of all, it needs to be that way to work. Second of all, I can come here to this y equals, and I now get this plot. x1t, y1t, and on and on. So x1t, I'm going to be ln of 4t. And for the y1t, it's going to be log, it's going to be 3 log of 2t, like that. Okay, so the top is ln 4t, the y is going to be 3 log 2 base 2 of t. And then I'm just going to go to second calc. Right, so second calc, the one right here, or second what does that say, trace. So second trace gives me to this calc right here, and I end up with these three. And I'm going to go to dy dx. right there, and hit enter. All right, you see it like this, and it's going to ask me to try to find where I want it at. And I can do that for just about anything, right? I can plug in 0, right? I can plug in literally anything I wanted there, but that's not what we want. What we want is the actual derivative itself. Now, how does that work? Well, it doesn't work. It's not that difficult. All you do is you just take the derivative of each of them. All right, so ln 4t, it's going to be 4t in the denominator, and then 4 in the numerator, which is going to be 1 over t. All right, and then for the second one, you have it's going to be 3 over t times the ln of 2, because that's the base. Or not, yeah, so you have 3t ln 2, so 1t, 3 ln 2 is still a vector, and we can keep going to the next problem. Okay. A curve is defined by parametric equations. X equals 4t to the negative 2 plus 4, and y equals 8t to the negative 1. What is d squared y over dx squared in terms of t? So what I'm going to do, right, is I'm going to find dx dt. And that's going to be negative 8t to the negative 3. And then I'm going to find dy dt, which is going to be negative 8t to the negative 2. Okay? Alright, now what? Well, I have a couple options. I can do dy dt over dx dt. Alright, that's what I can do. Alright, so dy dt over dx dt is going to equal dy dx, which is going to be negative 8t to the negative 2 over negative 8t to the negative 3, which is going to be t to the negative 2 over t to the negative 3, which is just going to be t. Dy dx equals t. Now I'm going to take that, so this dy dx is t. Dy dx is t. The derivative is t. The derivative of y with respect to x is t. Now I'm going to take the derivative of this, and it becomes take the derivative of this with respect to x, and it gets d squared y dx squared. Right? That's taking the derivative of t with respect to x. So what does that mean? That means that I'm going to end up with dt dx. dt dx is just going to be 1 over dx dt. Dx dt was negative 8t to the negative 3, so 1 over that is going to be negative 1/8 t cubed. Okay? That is how you could do that. Alright, that's how you would do that. And you'd end up with choice A right there. And we can keep going to the next question. Alright. Let R be the region in the first quadrant that is inside the polar curve 2 sine theta and inside the polar curve 2 sine 2 theta as shown in the graph. The curves intersect at theta equals pi over 3, which integral represents the area of R. Alright, let's see. Let's see what we have here. Alright, so if you draw a line from here to here, then this stuff in here, actually let me do that in a different color. So we're drawing this line here. The stuff in here in red is going to be defined by the blue curve. This is the blue curve, which is 2 sine theta. 2 sine theta. I mean, why did I say blue? It's red. Red curve, sorry. This is the red line inside the blue circle, which is going to be 2 sine theta. And then, of course, you have this part, which is in the purple curve, and that's going to be 2 sine 2 theta. So I can do 2 sine theta from 0 to pi over 3. And I can do 2 sine 2 theta from 0, or what, actually it's from, it starts from pi over 3, but right here, and then here it keeps going down until you get to pi over 2, I think. Yeah, pi over 2. So 2 sine theta 2 sine theta is 2 sine theta is going from 0 to pi over 3, right? And then 2 sine 2 theta is going from pi over 3 to pi over 2, which looks a lot like that one, right? So you have the 2's, you're squaring both sides, that becomes 4 and 4. You have to divide it by 2 because that's how the parametric polars work, so 2, 2, and that's our answer. And we can go to the next question. A particle moves in the xy plane so that at any time t is greater than or equal to 0, its coordinates are x equals 2t cubed plus 2 and y equals negative 4t to the fourth plus 4. What is the particle's acceleration vector at t equals 1? Well, I can take the second derivative of the x, and I get 3 and the 2, so I get 12t. And then for the y, it's going to give me negative 48t squared. So at t equals 1, that's going to be 12, negative 48. Right there. And we can keep going. Let R be the region enclosed by the polar curve r theta equals 4 plus 2 sine squared 3 theta, where pi over 4 is less than or equal to theta is less than or equal to pi. Which integral represents the area of R? Well, we're starting right here, right? We're starting right here. I think that's pi over 4, and we're ending up at pi. Right, pi over 4 to pi. Okay, pi over 4 to pi. That's it. Okay, so we can square this. 4 plus 2 sine squared 3 theta. Going from pi over 4 to pi. You have to square this part. Right? Is this what you end up with right here? Doesn't, let's see. You square that becomes 16 plus 16 sine squared 3 theta plus 4 sine 4 3 theta. Then you have to divide by 2 and you end up with this. Alright, so this is our answer. And we can keep going to the next question. Let f be a vector valued function defined by that entire mess. And we're trying to find the second derivative. Second derivative, well, okay, so if we try to find the velocity vector, right, at the whatever passes for the velocity vector, the first derivative, then you get negative 2 over t plus e, comma 6 over, what is it over? Well, it's going to be the 4t times ln base 4, but then you have to multiply by 4 in the numerator to get rid of it for the chain rule. So you end up with 6 over t times ln 4. Alright? And that is the vector. And that's the first derivative, so then you take another derivative, and you get positive 2 over t plus e squared, positive 2 over t plus e squared, comma what? Well, you have 6 over ln 4 times t to the negative 1, so it's going to become negative 6 over t squared ln 4. And that's going to be choice C, and we can keep going. Consider the polar curve r equals 2 tan theta over the interval 0 to pi. At which value of theta does the graph of r have a vertical tangent line? So that means it's not defined, really. Okay. Well, how do we go across doing this? Well, you split it into, you have to make it y and x. Right, so if you have a radius r, then the y is going to be, this is theta, then y is going to be sine. Right, so I can write y as 2 tan theta sine theta. And I can write x as 2 tan theta cosine theta. But since tan theta is just sine over cosine theta, that's just going to equal 2 sine theta. Alright, now the derivative of 2 tan theta sine theta is going to be 2 secant squared theta sine theta plus 2 tan theta cos theta, or just 2 sine theta. And that's going to be over the dx d theta, which is just going to be 2 cos theta. And then the 2's are going to cancel out. And you have secant, essentially you just have cosine theta in the denominator. So R has a vertical tangent line when cosine theta is 0, which is at pi over 2 and 3 pi over 2. So that's our answer right there. Oops. That is our answer, and we can move on to the next question. All right. Oops. The graph is discontinuous and so undifferentiable at those points. Well, if you think about it, that is correct, because secant squared theta doesn't work, does it? You can't do secant theta. You can't do secant squared theta at those points, right? Because here I have secant squared theta. You can't do that because it's going to be discontinuous. So that means you have no vertical tangents, and we can keep going. Here's the parametric curve. X equals t squared, y equals negative 4 tan t, which integral gives the arc length of the curve over the interval from t equals negative pi over 6 to t equals pi over 3. So negative pi over 6 to pi over 3, all of them do that. So you have the derivative of x, which is 2t squared, and you get 4t squared. So this one looks like it's good. And here you have a derivative of y. The derivative of y, that's going to give you 4 secant squared t, and then you square that and you get 16 secant to the 4th t. So that is our answer, and we can keep going. A particle moving in the xy plane has a velocity vector given by v of t equals cos 2t sine 2t for time t is greater than or equal to 0. What is the magnitude of the displacement of the particle between time t equals 0 and t equals 4? T equals pi over 4. Round to the nearest tenth. Okay. Well, see, the thing is that I can just find all of the vectors from this, right? So I can take the position vector to be negative 1/2 sine 2t, comma 1/2 cosine. Actually, yeah, it's going to be 1/2 sine 2t, then negative 1/2 cosine 2t. All right, now what? Now I can plug 0 into those. So I start at 0, negative 1/2, and I end up at, and with pi over 4, I end up at 1/2, comma 0. So I moved 1/2 in both of those directions. So in all, I would have moved the 0.7 units. And we can keep going to the next question. Let R be the polar function r of theta equals square root of 8 theta plus 1. What is the rate of change of the y-coordinate with respect to theta at the point where theta equals 2 pi? Well, let's see what we can do on polar first before we actually start messing around with anything else. Let's see what we can do. All right, and we can't do dy dx. We can't do dy d theta. Right, that would be nice, but we do have some options like this. We do have dr d theta. Right, now would that help? Well, we can actually try that later, but first we're just going to try. We're going to try plug this in as square root of 8 theta plus 1 times sine of theta times sine of theta. Okay, times sine of theta. That is one of them. Right, we're trying to find the rate of change of the y-coordinate with respect to theta at the point where theta equals 2 pi. So we can write the y-coordinate as square root of 8 theta plus 1 times sine theta. Okay, and we have to take the derivative of that. By we take the derivative of that by simply hold up, take the derivative of that by simply going to, where is it, n derivative, d theta, the function at 2 pi. All right, and what does that give us as our answer? Well, it gives us, it gives us 4 times the square root of pi plus 1. So that is our rate of change, and we can keep going. A particle moves along the curve xy equals 16, so that the y-coordinate is increasing at a constant rate of 2 units per minute. What is the magnitude in units per minute of the particle's velocity vector when the particle is at the point 4, 4? Okay. So how do we think about that? How do we think about what is going on in that situation? Right? Like what even is going on in that situation? Well, we have a vector, right? That the velocity vector is something comma 2. Okay, something comma 2. And the x coordinate of the velocity vector is going to be pretty all over the place all the time. All right, so this actually seems kind of like a related rates problem. Sorry, that seems like a related rates problem. That's what it seems like. You know, you have something moving, and you're trying to figure out this. Now I'm trying to figure out the magnitude of the particle's velocity vector when the particle is at the point 4, 4. Okay, so at 4, 4, how would we do that? Well, the thing we can see is that we can graph this as y equals 16 over x, and we can do window from 0 to 8, say, zoom fit, and we get something that looks like this. That's what it looks like. Now we can take the derivative dy dx take the derivative at x equals 4, y equals 4. And it's given to us as -1. But what does that mean? All right, is that the see that's not really the rate of change of anything in particular except dy over dx, right? But that's not the rate of change of either of the vectors, right? We're trying to do this in vectors. So if we're trying to think about this in vectors, we can actually change to parametric coordinates. Change to parametric coordinates, right? And we can see that if xy equals 16, all right, so if x of t, y of t equals 16, and x prime of t is something, and y prime of t is 2, then at some point in time where x of t and y of t are both 4, we're trying to find what x of t is, and then we can find the magnitude of the whole velocity vector. All right, so how do we approach this? How do we even do anything like this? All right, let's think. All right, so if we think about this, right, then we can realize that we're moving along the curve xy equals 16, and the y-coordinate is increasing at a constant rate of 2 units per minute. 2 units per minute. Okay, so at 4, 4, in the next say in 30 seconds, right? Because this y-coordinate is increasing at a constant rate, right? I think that's kind of important to remember. It's a constant rate, so it's going to go 4, 6, 8, right? Which means that the magnitude of the x vector is going to be it's going to be at 4 and then 16 over 6, which is 2.6, and then at 2. And we're trying to figure out how much it goes by. Right, so we can write this down as simply 16 over y, comma y. Where the velocity is going to be something, comma 2. Okay? So if we have our position vectors and then this, right? If we want to figure out how we rationalize that, well, we can make this, say, 2y, right there. And we can do 16 over 2y, which is just 8 over y. 8 over y. Take the derivative of 8 over y, and we end up with what? Well, we end up with negative 8 over y squared dy, which is going to be 2, so it's going to be negative 16 over y squared. Right, y squared is just the 16, so that's going to give us a 1. All right, now we put that into the equation, we get that squared plus the 2 squared, and that's going to give us 2 times the square root of 2 as our final velocity vector. And we can keep going to the next question. A curve in the plane is defined parametrically by the equations that x equals tan 2t and y equals sine 4t minus pi over 2. Find the value of dx dy dx at t equals pi over 2. All right, so this, we can just take our calculator out, we can plug in the equations. Tan 2t, right, we're still in we're still in radian mode, right? Make sure of that. And then sine 4t minus pi over 2. So tan 2t and sine 4t minus pi over 2. And then you find the dy dx at t equals pi over 2. And dy dx is 0. So that's our answer, and we can keep going. All right, let R be the region enclosed by the polar curve r of theta equals 2 theta sine theta as shown in the graph, which integral represents the area of R. Which integral represents the area of R? Well, we're going from 0, and then this is pi over 2. That should be pi over 2, right? That's pi over 2 right there, and then it keeps going. You get you come back down here to pi. And then when you go out from pi again, now you're going to negative, right? So it's going to just be going backwards, right? So it's really, this is just going from 0 to pi, and then it's going again. So see, I can draw that if we go to mode and polar, and I can make this R1, I can make that 2 theta sine theta. This is a good tool to remember where exactly stuff is happening. And I can make my window 0 to just pi, and my step is going to be pi over 8. It should always be something like that. And then I'm going to graph it. I should probably do a zoom fit. And it looks like this. That's the whole thing, right? That's the whole thing right there. Right, if I try to do less of it, if I try to do like 7 pi over 8 and do that, then I only get part of it. So I'm really just going from 0 to pi. So 0 to pi, I square this and I get 4 theta squared sine squared theta, like that, and then I have to divide by 2, so I end up with that. And that is our answer. And that is that for parametric equations for polar coordinates and vector valued functions. Hope you enjoyed this video or you learned something from it, and I'll see you next time we continue looking at more AP Calculus A, B, and BC topics. I'll see you then.